This video is the second part of determining the pH. The first part describes how to decide what type of solution you have and which calculation to use. If you don't know how to do that, please make sure that you watch that video. Let's continue.
Previously we saw that the pH is a measure of the hydrogen ion concentration of a solution. We know that this tells us the acidity or basicity of the solution. Remembering from our pH scale that numbers that are below 7 are acidic and those above 7 are basic, and if it is actually a pH of 7, then we end up with a neutral solution. We also know how to find the theoretical hydrogen ion concentration of various solutions. Now we're going to put that together and see if we can find the pH of a variety of different solutions. In the previous video, we identified whether the compound was an acid, base, or neutral. That was step 1. And we did step 2, which is identifying if we have a strong acid, strong base, or weak base.
And now we're going to look at steps 3 and 4, where we discover what the hydrogen ion concentration is, and step 4 where we find the actual pH from the given values in the question. That means that we're going to find some actual numbers. Again, these are theoretical numbers, which means that they are what we expect to see for the pH. They're not always the exact number that we would find, but importantly, they will have numbers. So we'll know if the number should be above or below 7, but we'll also know exactly how much above or below 7 it should be.
These are the questions from your lecture notes, with 2 additional questions added to the top. In the previous video, we identified these as acids, bases, and neutrals, and then separated them into their individual sections. We're going to continue with that identification system for this video. In our previous video, we looked to see if these acids were strong acids or weak acids. Then we were able to identify if we can find the hydrogen ion or the hydroxide ion, and then if it was equal to the number given or if it was between 2 numbers. If you don't recall how to do that, please go back and watch the previous video. As you may recall, the pH is the negative log of the hydrogen ion concentration, and so to do this calculation, we need to find the hydrogen ion concentration for each solution. In this video, we'll show you how to find the concentration of hydrogen for each solution, and then we're going to correlate that to the pH. Let's start with letter A. We see that we have HCl. It's a strong acid. It tells us the hydrogen ion concentration is equal, and then in this case it's going to be to 0.1 molar.
0.1 was the given concentration of the HCl. Because we know this is a strong acid, it ionizes 100%. That means that the hydrogen ion concentration is going to be equal to the acid concentration that we originally had.
That is equal to 10 to the negative 1. And then when we convert that to pH, that is equal to 1.
In this class, we're not going to be actually doing logarithmic scale. We're going to be using it, but we're going to use it in a simplistic fashion. Just as a reminder, when you take a log, what it's really looking at is the exponent. And so we're going to see this exponent here is negative 1. We're taking the negative log, so we're going to get rid of the negative sign. And we see that there's a 1, so the pH is 1. Now, if there were a number in front, a mantissa in this scientific notation, so if it was like 3 times 10 to the negative 1, the answer would not be 1 exactly. But because we are using 1 times 10 to the negative 1, we're going to look at this as 1.0. The 0.0 comes from the fact that the log of 1, the 1 times 10 to the negative 1, that log of the first number, the mantissa, is going to be 0. So that's how we get 1.0. At any rate, what we're going to do in this class is we're just going to look at that exponent. We're going to ignore anything that would be in front of the exponent, and we're going to just use that exponent to find the pH. So in this case, our hydrogen ion concentration is 10 to the negative 1, so our pH is 1.
Now you try letter B. Pause the video while you get the answer. On letter B, we have 0.001 molar HNO3 we're trying to find the pH of. HNO3 is a strong acid that tells us the hydrogen ion directly. It's strong, so we're going to put an equal sign. The number is 0.001, which we're going to change to 10 to the negative 3, and that means the pH is 3. Letter C is a little bit more challenging. We have what is the pH of 0.01 molar HF. HF is a weak acid. It is an acid, so it tells us hydrogen ion, but because it's weak, it's going to be between two numbers. It's going to be between the number it would have given you if it were a strong acid, which is 0.01, which we see in the question, or 10 to the negative 2, and what would happen if there were no acid added, which is 10 to the negative 7, the same as pure water. So if those are the hydrogen ion concentrations, what are the pHs? Well, if it were a strong acid, it would have been 2. But in this case, it's a weak acid, so it's between pH of 2 and a pH of 7. Now let's look at letter D. This question is a little bit different because it's asking which one has a higher pH. So we have to look at the two parts, see what the pH is for each of them. For the first one, we see it's a weak acid. It's an acid, so we know it's going to tell us hydrogen ion directly. It's weak, so it's going to be between, in this case, 10 to the negative 2 for the strong acid, and 10 to the negative 7 as if it were water. Again, this is a weak acid, so it's between those two numbers, and that tells us that the pH is between 2 and 7. When we look at HI, it is a strong acid. That means the hydrogen ion concentration is equal to the original concentration, which in this case is 10 to the negative 2, which means that the pH is equal to 2. So here we see the question is actually asking which one is higher. So for the weak acid, it's somewhere between 2 and 7. For the strong acid, it is 2. Hopefully you can see that a number between 2 and 7 is larger than the number 2, and so we find that there's a higher pH for the 0.01 molar HF.
And finally, let's look at letter E.
This one's a little bit tricky because the way it's worded, it is a little bit different. It says, what is the theoretical pH of a solution of hydrogen acetate which has a hydrogen ion concentration of 0.0001 molar? Now, the reason this one's tricky is I asked you to look to see is it an acid, a base, or a neutral. And again, you would say it was an acid. And then I say look to see if it's a weak acid, and this one is a weak acid. So normally, because it's a weak acid, we would say it's between two numbers. But notice that in this question, it does not tell you what the concentration of the original compound is. It just says it has a hydrogen ion concentration of 0.0001 molar. So what we're going to do with that is we're going to use that directly. Our hydrogen ion concentration is equal to 0.0001 molar. It doesn't matter what the source of the hydrogen ion is in this case. It's saying this is the concentration. And so we're going to write the hydrogen ion concentration as 10 to the negative 4 molar, which means that our pH is 4. Now let's look at the bases. So we know for bases that it can tell us the hydroxide ion concentration directly. It does not tell us the hydrogen ion concentration directly. We also know that the pHs should be above 7 because they're basic solutions. And finally, we need to remember that for bases, to find the pH, we're actually going to find the pOH. pOH, again, is defined as the negative log of the hydroxide ion concentration. And the big thing we need to remember is that the pH plus the pOH is equal to 14. So let's start with letter F. It asks, what is the theoretical pH of a 0.1 molar solution of NaOH? Again, this is a strong base. It's a base, so it's going to tell us hydroxide ion concentration. It's strong, so it's going to be equal to the original concentration of the NaOH. In this case, the hydroxide ion concentration is 10 to the negative 1 molar. From that, we can find something called the pOH. Now, the pOH is going to be 1. Just like we saw with the pH, it is just going to be the negative log of the molar concentration of hydroxide in this case. From that, we can find the pH by subtraction, recalling that the pH plus the pOH is equal to 14. If the pOH is 1, That means the pH must be 14 minus 1, or 13. And now it's your turn to try letter G, which is, what is the theoretical pH of a 0.0001 molar solution of KOH? Pause the video while you try this, and then come back to me. Here we have a strong base, so that's going to tell us hydroxide ion. It's strong, so it's going to be equal, and in this case we have hydroxide ion concentration of 10 to the negative 4 molar, which means my pOH is 4, and then we find the pH by subtraction. In this case, that's 14 minus 4, and our pH is going to be 10. And letter H is a little bit different because now we have a weak base. So letter H says, what is the theoretical pH of 0.001 molar solution of ammonium hydroxide? Again, that's a weak base, but it is a base, so it's going to tell us that the hydroxide ion concentration. In this case, it's weak, so it's not going to be equal to, but it's going to be between what it would have been if it was strong, and in this case, that's 10 to the negative 3, and what it would be if there were no base present, which is 10 to the negative 7, which means that our pOH is somewhere between 3 and 7. So now to find our pH, we just have to convert from pOH to pH. So you're going to subtract both of them from 14. So in this case, we'll have 14 minus 3, which is 11, and 14 minus 7, which is 7. Therefore, our pH will be between 11 and 7. And most people would actually say it's between 7 and 11 because we normally count upward. It's numerically the same, but it makes people feel better to say between 7 and 11. Now let's look at letter I, which has a different question. It says, which one has a higher pH, 0.001 molar NH4OH or 0.001 molar LiOH? Notice that they are both the same concentration, and they are both bases, but one is a weak base and the other is a strong base. I'm going to break this into two halves. Because they're both bases, both of them will tell me hydroxide ion directly. For the weak base, the first one, we're going to see that it will be between, if it were a strong base and a neutral substance. In this case, that means the hydroxide ion concentration is between 10 to the negative 3 and 10 to the negative 7. That means in this case that the pOH will be between 3 and 7, and that means that the pH will be between 11 and 7. For the strong base, again, we're going to see the hydroxide ion concentration, but it's going to be equal to the answer we see here. That will be 10 to the negative 3 molar. That means the pOH is 3, which of course means that the pH is 11. So we see that we have a higher pH for the lithium hydroxide. For these types of questions, I always give you the same concentration of the starting material, so you don't have to worry about any of that, but you do need to look at the comparison of the answers. When we look at letter J, it asks, what is the theoretical pH of a solution of ammonium hydroxide which has a hydroxide ion concentration of 0.00001 molar? It is a base, so it's going to tell us hydroxide. Now, this one's a weak base, and so normally we would say it's between two numbers, but if you read the question carefully, it says it has a hydroxide ion concentration of that number. So that means it's already telling us what the hydroxide ion concentration is. It is not going to be between two numbers. In this case, the hydroxide ion concentration is 10 to the negative 5 molar, and that means that the pOH is 5. That means that the pH is 14 minus 5, which is equal to 9. So how do we find the pH of a neutral solution? In this case, we have the question, what is the pH of a 0.001 molar KCl solution? KCl is neutral because it's not an acid nor a base. What do you do for this? Well, recall that for neutral solutions, that the concentrations of the hydrogen and the hydroxide ions are equal to each other. The only way that they can be equal is if they are both 10 to the negative 7. So to find the pH of this solution, all we have to know is that the hydrogen ion concentration is going to be 10 to the negative 7. The actual concentration of the neutral substance makes no difference at all, because it doesn't give off hydrogen or hydroxide, it doesn't matter what the concentration is. We know that because it's neutral, the hydrogen ion concentration will be 10 to the negative 7, and of course the pH will be 7. Now the last one's a little different. It's asking us to figure out the theoretical pH for other solutions. We're actually going to, the question doesn't actually ask us that, but we're going to look at it and see if we can figure it out. For this one, the question says, which has a higher pH, 0.001 molar hydrogen fluoride or 0.001 molar ammonium hydroxide? The main key to this question is to decide, do I have an acid, base, or neutral? And that's going to actually be able to answer the whole question. You don't have to do the full calculation, although I will show you how to do the full calculation. So for this, we see that the first one, the HF, is an acid, and the second one is a base, the NH4OH. And so what we're going to see is that, if you recall, acids are always below 7, and bases are always above 7. So without doing any calculations at all, you could determine which one has a higher pH. The HF is below 7, the ammonium hydroxide is above 7. Obviously, something above 7 is higher than something that's below 7, and so the ammonium hydroxide is the answer. It is the one with the higher pH. Now let's go ahead and do the calculations so you can see how to do them. A little extra practice. Please try to find the pH for each of these solutions, pausing the video while you do so, and then come back and I'll show you the answer. Alright, so let's look at the HF first. Again, we're going to cut this into two pieces. We see that the HF is an acid, which tells us the hydrogen ion concentration directly. We see that it's weak, so it's going to be between two numbers. In this case, it's going to be between 10 to the negative 3, that's what it would have been if it was a strong acid, and 10 to the negative 7, which it would be if it were neutral. So it's between those two numbers. That means that the pH is between 3 and 7. For the base, we see the same basic concept. We see that it's a base. Instead of giving us the hydrogen ion directly, it's going to give us the hydroxide ion. And so our hydroxide ion concentration is between two numbers because we have a weak base.
10 to the negative 3 and 10 to the negative 7.
Well, it sounds like it's the same answer, right? But remember, this is the hydroxide ion concentration. We have to convert that to hydrogen ion concentration. The easiest way to do that is to just convert it to pOH. So our pOH is between 3 and 7. And now convert that to the pH, which again is being subtracted from 14. So our answer is that the pH of the 0.001 molar NH4OH is going to be between 11 and 7. So hopefully again you can see that the number between 11 and 7 is higher than the one that's between 3 and 7.